Okay, welcome back. So in the last little installment, we determined that the force acting on the bottom of the tank due to the static pressure of the fluid in the tank was simply equal to rho g h l w, or equal to the weight of all of the fluid contained within the tank, and that it acted through a resultant force located at a y coordinate of equal to L over 2. So in the next example, we're going to look at how this static pressure acts on the vertical walls of the tank. Now, remember that the static pressure equilibrium equation, or the equation of fluid static equilibrium, is given as rho g minus grad p is equal to 0. Okay, stating that the gradient of the pressure is linearly equal to the acceleration field times times density. My mistake. Sorry, guys. I've been at a conference all day and I'm tongue-tied. So what this tells us is that dp dz is equal to rho g, or magnitude of g, or that it varies linearly in the z direction. And this should be negative because gravity is pointing in the negative z direction, which is why we've gone ahead and drawn these pressure distributions acting on the wall as these linear gradients. Okay, oops. Now, once again, went ahead and did this in the last lecture as well. Go ahead and assume that the pressure at the free surface is 0, which is why the pressure here starts at 0, and it moves down to the bottom here, where the pressure is equal to gamma h, or rho gh. Note, this is the same thing we computed, rho gh. Remember, we already computed this in the last section when we calculated the resultant force acting on the bottom of the tank. Again, pressure is a scalar. Whether it's acting on this wall or on the bottom of the tank, it's the same because it acts equally in all directions. It's isotropic. Okay, so the first thing we're going to do is try to calculate the total force, or the magnitude and direction of, of the resultant force acting on the wall of the tank. So let me Okay, great. So we're going to look at the vertical walls of the tank. And part 1 is going to be calculating the pressure distribution on the wall. I just talked through this while we were in the PowerPoint slide, but let's go ahead and do it formally. So remember, rho g, vector form, minus grad p is equal to 0, signifying that grad p is equal to rho g in vector form, which in this case, because gravity is directed downward and z upward, is equal to 0I plus 0j minus magnitude g k. So we have that partial p partial z is equal to negative rho g. Okay? Thus, because the pressure at any point along the wall here can be represented by integrating from the free surface to that point. So p at some x, y, z, we're going to go ahead and say is equal to our starting pressure plus the integral from this is going to be a path integral from 0 to x grad p times ds, that is the distance along this path, and we'll get into this more later, which in this case is simply equal to, because grad p contains only one component, that is along the z-axis, this will be equal to zp naught plus 0 to z1, or 0 to z rather, of dp dx times dz. And because dp dx is constant, that is dp dx is equal to negative rho g, we can write this simply as p naught minus rho g z minus 0, or just z. And p naught we've been told to ignore, so that goes to 0. So once again, this is like the 8th time we've derived this. P of x, y, and z simply turns into p of z equal to negative rho g z. Okay, so that's the pressure distribution acting along the wall. Increases with depth, that is with increasingly negative values of z. So the next question is, let's find the total force. How do we do that? Part B, total force, or we're going to put this in vector form this time, or resultant force F. So before we do this, I'm going to go ahead and explain the vector notation that we're using here. If we consider a little element of this tank wall here, let's go ahead and okay. So this is a little cut for a tank wall, and the fluid is on this side. We'll go ahead and say liquid, not just any fluid. And this is the air. Then we're going to go ahead and specify the normal vector of this wall as pointing outward into the fluid. That is, in this picture on the upper right, the normal is pointing into the water. The pressure, on the other hand, is acting outward, that is trying to push the wall away from the fluid. And so that means that the resultant force is acting in a direction opposite to the normal on the wall. So in the wall coordinate system here, our little elemental force acting on this, if this has an area of delta A, then delta F is equal to P times delta A times negative normal. All right, so let's go ahead and compute the total force acting on this. So the resultant force can be computed as the integral over the area of this elemental force, right? This differential force. And since we just showed this differential force over here as being equal to the pressure times the differential area times negative n, we're going to go ahead and say that Fr is equal to area P, and we're going to go ahead and leave this in very general spatial as a function in space, times normal in x, y, z. I write normal as a function of space because later we're going to move on to curved surfaces where the angle of the normal vector may change at different points along the surface. Right now we're dealing with planar surfaces. We don't have to worry about it. Normal is going to be considered a constant, but in the next lecture that won't be the case any longer. Okay, times the A, and remember that the differential force is actually equal to negative P times this differential A times normal, so we'll move this negative sign out front to account for the fact that the pressure and the normal point in different directions. So in the case under consideration, since the normal points in the negative J direction, we're going to go ahead and write this as force resultant is equal to negative integral over the area of P x, y, z times negative j times dA. These two negative signs, of course, canceling each other out. Oops. Giving us a force that is in the positive direction. That is exactly what we expect if we're looking at the wall on the right-hand side. Okay, I'll leave it to you to calculate the force on the left-hand side wall if you so choose, but the same reasoning is going to apply. So let's go ahead and actually plug in known values for the pressure. It's equal to integral over the area of negative rho g z times dA times j. Integral over the area. Now we're going to go ahead and plug in the limits for this integral. So instead of just leaving it as a generic area integral, we'll go ahead and say that it is from 0 to w, that is the width going into the page, and from negative h, that is the negative depth of the fluid, to 0. So integrating from the bottom of the tank to the free surface, or along the positive z direction, negative rho g z dA times, again, our vector direction. So let's go ahead and, this dA should turn into a dz dx. So let's go ahead and deal with this outer integral first. Of course, nothing in here is a function of x, so we can simply take care of that in one fell swoop. So turn a single integral, negative rho gz times w times dz j. And now integrating this gives us negative rho g z squared over 2 w evaluated from negative h to 0 times j, which will turn into rho g h squared over 2 w j. All right, couple things I would like to point out about this. This can be a very informative result for a few reasons. Let me go ahead and box this in. I'm going to introduce a concept called the pressure prism right now. So if we look at this distribution of pressure along the wall, said earlier, it takes on this triangular form, right? So this side has H. The pressure acting at the bottom is rho GH, and then this is acting along a wall that is W wide. So note that the resultant force is actually equal to the volume of this prism. That is, the area of this is 1/2 rho GH times H, or 1/2 rho GH squared, and it is multiplied by the width of the prism. So this is a really informative concept because we'll find that we can use it on a lot of different cases. In fact, things like the centroid of this prism and are going to inform us as to where pressure acts on surfaces that are planar. So we'll get into this more a little bit later, but I encourage you to mull this over and think about how really nice and intuitive this fact is that if we represent the force as a sort of a curve, then the integral under that curve gives you the resultant force. Or if we think of pressure as a curve. Okay? So there's another way to think about this as well, and this is the one that is even more important than the pressure prism. We can go ahead and write the resultant force is equal to rho g h over 2 times wh. Now let's go ahead and split the terms up here such that this is the pressure at the wall centroid, and this is the area of the wall This wall is h high, therefore its centroid is at h over 2, which means that rho g h over 2 is the pressure evaluated at the wall center, and giving us that pressure, multiplying it by the area of the wall, gives us the resultant force. So this is actually a very general result that applies to all planar surfaces, and we'll get more into the generality as we move on to planar surfaces at inclined angles. But before we do that, let's go ahead and compute, if you haven't guessed already, where does the resultant force act? Okay. So again, we're going to deal with this by the method of equivalent moments, but before we do that, let's talk about how we deal with moments in vector notation. Now, you're probably familiar with this already, and I'm probably being redundant here, but because you've all taken dynamics of some flavor. But you may remember that moment is actually a vector quantity, and it is equal to the moment arm, we'll call that r, times resultant force. All right? So this can also be written out as the integral, in this case, over the area of r, x, y, z times differential of force. Okay, but if we go ahead and look at this cross product here, then in the case we're considering, right, we have the force is acting only in the positive y direction, so it has only a j component. 0I plus magnitude force along j plus 0, k. So what that means is that moment arm times, or cross with the resultant force, is going to be equal to negative magnitude Fr times Zr I plus 0j plus Xr times magnitude of Fr times the k unit vector. All right, so what this means is that this is the moment component along the x-axis. This is the moment component along the z-axis. So in order to find the location of the x-coordinate of the location of the resultant force, we sum moments about the z-axis. And in order to find the location of the resultant force in the z-coordinate, or in the x-coordinate, we sum moments about the z-axis. I'm sorry, I said the same thing twice. To find the x location, the z location, we sum moments about the x-axis. Got it backwards. So this also means that we've got two unknowns here. Where does it act in the z and x coordinates? So first, let's go ahead and solve for the x location of the resultant force. So we know that xr times the magnitude of the resultant force, sorry, I dropped the, is equal to the integral negative rho g z times x times dz dx, where this will be an integral from 0 to w and from negative h to 0. Okay. This will in turn allow us to, again, we are assuming that these components are, sorry, not the z, assuming that this component, yes, that this component is constant, so we can move it outside of the integral, giving us negative rho g, 0 to w, negative h to 0 of zx dz dx. Okay, so let's go ahead and perform this integral, and I'm not going to go through the details, but what you'll end up with is this will come out to rho g h squared over 2 w squared over 2. Now remember, this is the total moment, the resultant moment, not the resultant location. Let's go ahead and divide by the total force. So if we xr fr divided by the magnitude of fr, we get rho g h squared over 2 w squared over 2 divided by rho g h squared over 2 w. All this cancellation that occurs is going to give us simply w over 2. Should be no surprise, as I explained earlier, the pressure is constant along the x direction, right? There's no gradient in the x direction, and so it acts in the center of the x extent of the tank. Okay, so we computed the center of or the resultant force location along the x-coordinate to be w over 2. Pardon the gap there. There was a little math error that I had to cut out, so hopefully that wasn't too disruptive. But let's go ahead and now calculate the center of the, or the point of application of the resultant force along the z-axis. That is, how high along this wall does it occur? So, z location of resultant force. Oops. Whoa. Okay. So again, we're going to use the equivalent moment formulation here, where we can say that the resultant z times the magnitude of the resultant force is equal to the integral over the area of z times our little differential force here, right? And this little differential force is pointing in the positive direction. We already showed that the misalignment of the pressure and the normal are canceled out by the fact that the normal is pointing in the negative y direction, so the net is positive. So we're going to skip over the, we're going to leave out the negative signs here, and I'll let you sort those out as you see fit. But this is going to give us the integral from 0 to w, negative h to 0 of z times rho g z. This is, of course, negative, the pressure times differential area, dz dx. Okay, we'll go ahead and move this component here outside of the integral, so it gives us negative 0 to w, negative h to 0 of z squared dz dx. Oops. Let's not forget the rho g there, negative rho g. Okay. And so let's go ahead and evaluate this integral to get rho g 0 to w z cubed over 3 from negative h to 0 dx, which will give us negative rho g 0 to w h cubed over 3 dx. All right, and then integrating along the x direction simply gives us negative rho g h cubed over 3 w. Okay, now dividing through by a resultant force to isolate the z component, we get zr is equal to negative rho g 3 w divided by, again, let's think of it in terms of that volume of that prism, 1/2 rho g h squared w. Now we get some cancellations going on. Get rid of that exponent, get rid of that h, w gone, rho g gone, leaving us with negative 2h over 3. All right, so does this occur above or below the area centroid of that wall? The answer is below the centroid. Okay, this is a major result. Why? Why does this happen? Well, because the pressure increases with depth, more pressure induced force acts along the lower portions of the wall. This should be fairly intuitive. Okay? So think about, if this is the center of pressure here, center of pressure, think about how we computed that. Okay, we figured out what the total moment induced by the pressure forces on the wall was and divided through by the total pressure forces. In early courses on ship design, you probably run across weights and centers and use the same thing to find the mass center or the center of gravity of a ship. You add up the moments caused by the masses of objects on the ship, divide through by the total mass. The same thing is being performed here, only we're using forces and pressures. Okay? So, remember earlier, we chose to assume that the outside pressure here, the atmospheric pressure, is equal to 0. Why is that? Doesn't the choice about atmospheric pressure make a difference? Are we by assuming that it's 0, are we neglecting some component of the pressure that's acting on the wall? Well, the answer is yes, but because this pressure is occurring outside, we're assuming it's constant everywhere, and so it's actually acting on the wall on both sides. So if we come back to look at the idea of gauge and absolute pressure, what we can see is on the left here is the side, or is the case that we just considered, where pressure is equal to 0, and so the gauge and absolute pressure are equivalent. On the right here is what happens if we include atmospheric pressure, and what you should hopefully see is that the atmospheric component cancels out on opposing sides of the wall. So while it does act on the wall, it acts equally on both sides of it, meaning that when we're computing resultant forces, we have only to consider the gauge pressure. We don't need to worry about the ambient outside pressure because it acts equally everywhere. Okay? So that wraps up our discussion of how to calculate the forces on the planar surfaces that are either horizontal or vertical. In the next case, we're going to look at inclined surfaces, or those at an orientation that is neither horizontal nor vertical.